So, okay, good afternoon, my dear students. So, today we'll be studying this chapter due to some technical issues. I've started it again. Okay, so this is the chapter thermal expansion properties of matter. This is our today's goal. So, as at first we'll be understanding about temperature and scales, temperature scales, thermal expansion, and calorimetry. Okay, so let me check what's going on the YouTube. Is it live stream there or not? Yeah, it works. Okay, so let us start with the first topic. So at first, today will be this topic, that is scales of temperature. Scales of temperature. Yes. Okay. So first of all, you must understand this thing. See, this session which we have organized this session. It's like a one-shot class. So we'll try to complete a majority of the things in this one session. So we'll not go into the depths of the theories. Basically, we'll take a lot of previous year numericals from the NEET, competitive exam. So let us start. So if somebody is asking from me, what do you mean by temperature? What do you will say? That what is temperature? So simple temperature is, it's a measure of hotness and coldness of body. You students already know this thing. So if we just somebody is asking from me, what is SI unit of temperature? So basically, SI unit, you know this thing, the change in Kelvin and the change in Celsius, scale are both same. But here by default, I'm taking throughout the chapter as Kelvin here. Okay. Okay, now let us proceed. Celsius scale. Celsius scale. So we know this thing, temperature is a measure of hotness and coldness of body. But now the question arises, how do we measure this temperature? I mean, there must be some measuring tool and all those things. So we know this thing, to measure the temperature, we have thermometer, isn't it? Thermometer is also calibrated on different scales. We have the Celsius scale, we have the Kelvin scale, we have the Kelvin scale, we have Fahrenheit scale too. We have Fahrenheit scale too. Okay. So now we'll understand what's the calibration on as per these scales. Okay. So let me draw it first. Copy this. I think I need to draw it again here. Okay. So now, suppose, these things which I've drawn here are like, this is the topmost calibrated point and this is the lowmost calibrated point for the respective scales, whether it's Celsius, Kelvin, or Fahrenheit. Cool. So now if you see, the topmost is steam point. And this in Celsius, it's calibrated as 100 degrees Celsius. And the bottommost point is ice point. And it's calibrated as 0 degrees Celsius. If we see the divisions in between 100 and 0, now if we see the divisions between 100 and 0 degrees Celsius, so total divisions are basically, yes, these are 100 divisions. Okay. The same will call for all other scales too. So on the Kelvin scale, the steam point in the Celsius is 100. On the Kelvin, it is 373 Kelvin. Okay. And this is 273 Kelvin. And difference between these are equals to 100 units. I mean, the same difference. If you minus 373 minus 273. Cool. This is 212 degree Fahrenheit. And this is 32 degree Fahrenheit. The difference between these two, if we check it out, is 180 units. Because 212 minus 32 is, I think, 182. 180 only, isn't it? So here we have generated the scales. Okay. Now we need to do some calculation. So there is a method of basically conversion of temperature from one scale to another. Let's understand that. Suppose if you want to convert, let me write this topic here. Okay. So I can write here, I can erase this and write it here only. It works. So it's conversion of temperature from one scale to another. Now let us understand the method that for any scale, what's the method we can apply so that we can do conversion of temperature from one scale to another. This is our demand here, okay? We need to do this. So how are we going to achieve this? Let us understand. So what we'll do, suppose I want to measure at this point. Okay, let me use a different color for this. Suppose I want to measure at this point. Let me mark here the temperature is suppose some C degrees Celsius. And for the same division here on the Kelvin scale or in the Kelvin scale, it's like something as here, it's K Kelvin. Okay. And for the same and the Fahrenheit scale, it's, F Fahrenheit. Done. So now let us apply the formula. So what's the formula is, what do you do? First you will write this C minus the lowest point. I mean the ice point in the Celsius scale is what? This is a Celsius scale. So ice point in the Celsius scale is what? It's 0. Upon total divisions are 100. Done. And on the Kelvin scale, if we see, the division is K because I want to measure at the same point what the Kelvin temperature is. And the lowermost point is here as 273. Okay. And the total divisions are 100. Similarly, here, if you see, we have F as Fahrenheit and 32 degree Fahrenheit as the lowest temperature, and total divisions are 180 units. Done. So now let us solve these equations. I mean, this basically behaves as constant. So this is a methodology here. This everything which I've written here, it's been written here this method is constant. I mean, these four conversions or four quantities are basically constant. So we can compare each of them and can get the results. Done? Let's approach. So first it says C minus, I mean C upon 100 because it's 0. So C minus 0 is again 0. First, K minus 273 upon 100. Okay. So when you will solve this, you can see what we will be able to get the answer as K C plus 273. So you must always remember this, okay? Never forget it. Always remember this. So K is equals to C plus 273. This is our derivation here. So if suppose, if I say, let's measure for the boiling point, that is 100 degrees Celsius. So when we insert this, we get K as 100 plus 273. This answer is 373 Kelvin. Minus 32. We will solve this. This is 2918 to 10. With minus 32. Please remember this also. Please remember this also. So a third is, see, I'm not going to convert for you. No, we can convert. You know this thing. K is C plus 273, so you can put C as K minus 273, and then you can get the answer, isn't it? So if we can do this too. So I will write here from here. What I'm going to do is this. I'll place it here. So C comes out to be K minus 273 is equals to 5 by 9 F minus 32. Done. And then you can solve and you'll get the respective K and F comparisons on the scale, basically thermometer calibration. And there is one more thing which is known as absolute zero. What is this absolute zero if somebody is asking from you? So you'll tell on the Celsius scale, if the temperature is minus 273 degrees Celsius, or on the Fahrenheit scale, if it's minus 460 degree Fahrenheit, then on the Kelvin scale, you'll get the perfect equivalent as 0 Kelvin, 0 Kelvin. And this 0 Kelvin is basically your absolute zero. See why the word here is given as absolute zero? The reason for this absolute zero thing is, on the universe, we see in thermodynamics, the 0 Kelvin temperature is not possible. I mean, if we say the statement, because 0 Kelvin temperature shows this thing, everything is like still, nothing is moving, and it's not possible. The universe can't be static. Okay. And we know it's expanding. Entropy is greater than zero if we prove via thermodynamics. Okay, so these are the few tools which will be helping you in solving the numericals which are on your screen here. So your first numerical is here, dear students. Yes, so this is the numerical. Question number 1. I'm writing it here, please solve it. So we have four options, dear students. You have to find the answer that at what temperature, basically the temperature in Celsius and Fahrenheit equalize. So what's the temperature is? It's your, it's a question for you, numerical question. Please solve it. I'll be providing you the solution in within 1 minute. But first you have to solve it and give me the answer. Okay, so I'm going to solve this now. We know this thing. If we want to convert the temperature from Celsius to Fahrenheit, what we can do? We're having a formula that is F minus 32. Okay. So here they have given us a very cool thing. Celsius and the Fahrenheit equalize. So let us make use of it. So we can assume C and F as same because they are equalized, isn't it? So when we use this, we get the value as C is X. F is also what? It's X minus 32. Let's use this. This is 9X. This is Fx minus 5 into 32. Now if you see this, 9x minus 5x is equals to minus 5 into 32. We know this thing, if we multiply minus 5 into 32, we get what? 160. Isn't it cool? Yeah, so when you'll solve this, this is minus 160. 9x minus 5x, you'll get it as 4x minus 160. So x comes out to be minus 40. Then, so our answer is what? Yeah, true. So our answer is this, that is minus 40 degree. Okay, so it's a basically here number. Understand this. This is basically a number here. Okay, let's move next. So here you are having a next question in front of you. Next question in front of you is here. Basically question number 2. I'm writing it here for you. So please solve this now. I'll be giving you the solution here. You have 2 minutes to solve this problem 2. So time has started. So, okay, let us solve this question. Your time is up. Again, here it says the temperature on a Fahrenheit scale and Kelvin scale are same here. Cool. So let us solve this. Kelvin and Fahrenheit, now both these are same. So I can assume this as X number. We know this thing, Kelvin is equals to Celsius plus 273. So I can place this value here. It's X is equals to C plus 273. C is equals to what? C is X minus 273. Okay. So, okay, students, just be on hold 1 second. Okay, so now let us solve this equation. So C is equals to 5 by 9 F minus 32. Okay. Now if we see C is equals to from this equation, if we need to solve it, this comes out to be, okay, let me do a little bit. X minus 273, 5 by 9, X minus 32. Now let me solve the complete equation. Students, when you solve, will you solve this equation? No. Your answer will come out to be 574.25. This is your answer, okay? Okay, next question for you people. Question number 3. Try to solve this. Okay, students, you have 2 minutes for solving this numerical. Then I'll be providing here solution. Okay. Okay, students, so time is up. Let us solve this. So if you try to understand the numerical, it says the freezing point of a thermometer marked as 20 degree. The freezing point is marked as 20 degree, and the boiling point is marked as 150 degree. So freezing point is 20 degree, boiling point is 150 degree. A temperature of 60 degrees Celsius on this thermometer will be read as what? So it's something a random scale, isn't it? It's something as a random scale. So let's solve this question. This is 150 degree. This is 20 degree. This is in X, random temperature. This is 0 degree Celsius. This is 100 degrees Celsius. This is something is 60 degree. So this I'll call it as Celsius scale. And now we'll apply the same approach before which we apply to some other scales. Okay, so what's the approach is? Before applying that, let me check the divisions here. It's too important, isn't it? So if you check the total divisions, so between 150 and 20, the total divisions are, yes, 130. And of course, it's a Celsius scale. The divisions are 100. No worries in that. Let's apply the approach, the constant approach, the constant method. So random temperature X minus the lowest point temperature, or the lowest temperature 20 upon total divisions as 130 equals to, it's a constant which is equals to, the random temperature here it's already given 60 minus 0, total is 100. So this goes on deletion, and then let's solve this equation. Okay, this also goes because this is of no use here. So X minus 20 upon 13. Let's cross multiply this. 6 3 is 18. It's 78. Okay. So we get the answer as X minus 20, 78. If you solve this, you'll get X as 20 plus 78. Your total answer is 98. Okay, this is your answer, 98 degree. So our option is C option is the right answer. I hope you were able to find the answer. Let's move towards the next question. So this is a very good level numerical for you students. I'm writing here the question. Question number 4, the fourth question. Okay, so students, the question is in front of you on your screen. This is the fourth number numerical. Solution I'll be providing you in 2 minutes. So you have 2 minutes to solve this question. Please solve it. So dear students, question is very simple. You're having a random W scale. I mean, it's not Celsius, it's not Kelvin, neither it's Fahrenheit. It's some random scale. Okay, so we'll say let's draw the scale. Now the topmost temperature is given as 239 degree W, and this W is neither Celsius, Kelvin, whatever. Okay, and then it is the lowest is given as 39 degree W. So we have to take a random temperature. That's a simple approach, X. So corresponding to it here, we have our Celsius scale as per the question. I hope you have read the question, isn't it? 100 degrees Celsius. And here the lowest is 0 degrees Celsius. And here in between, the temperature calculates to be 39 degrees Celsius. Now, when you will solve this thing, we know the approach. Random x minus 39 upon 200 is equals to 39 minus 0 upon 100. So x minus 39, 2 into 39, x is equals to 78 plus 39, which itself is equals to 117 degree W. Okay. Let us go for change in temperature. So here we are having 100 degrees Celsius temperature, the topmost. Here we are having 0 degrees Celsius. Here we are having 373 Kelvin. Here we are having 273 Kelvin. Here we are having 212 degree Fahrenheit. Here we are having 32 degree Fahrenheit. Cool. So if we go from here to here, we're having 100 degree divisions. I mean 100 divisions basically. And between these two, if we check it out, we again are having the 100 divisions. And if between these two we check it out, we're having 100 divisions. Not 100, it's 180 divisions. Now, if we need a direct formula for change to find the change in temperature. Suppose the numerical comes in such a way, they are directly asking you to find the change. So what are you going to do? So first here, you must understand this thing, change in Celsius is always equals to change in Kelvin. Got it? Second, if you check, change in Celsius is equals to 5 by 9 change in degree Fahrenheit. This also you must remember. Please remember both of these things, okay? It's very, very important. Remember this. Now, K is equals to C plus 273. So I can do differentiation. Let's generate a derivative from this above equation, okay? So when I have generated a derivative, this gives you C as 5 by 9 F minus 32. Cool. So now you can see here, from here I'm getting this as this, so I can write directly, if somebody needs a derivation kind of thing, so you can check it out from this. And now if I'm generating a derivative of this gives me dc upon 5 by 9 df, because the rest of the things are constant, so this goes to 0. Now the small, infinitely small change can be converted to delta, so here we're having the answer in front of you. If somebody is just they want the derivation thing, you can get it from here. So basically we are having two equations. Your equation number one, that is delta c is equals to delta k. It stands for the change in Celsius scale is equals to change in Kelvin scale. And here the change in Celsius scale is equals to change in Fahrenheit multiplied by 5 upon 9. You must remember this factor, it's too important. 5 by 9. Okay. Now let us solve the question. So here in front of you, the question number 5. So again, you're having 2 minutes to solve this question. Then I'll be providing you the solution here. Okay, please solve it. Okay, so now I'll be solving it. Your time is up. We know this thing. I hope you have read the question and try to solve it. So we know this thing, change in Fahrenheit is equals to what's given here. If you check out this calibration scale is 212 degree Fahrenheit. It's 140 degree Fahrenheit. So if you check out the change, it's 140 212 minus 40. So what's the total value is? It's 72. Okay. So here we have 72 thing. Now we say del C 5 by 9 del F. So this is equals to 5 by 9 into 72. You'll get the value as 40 because you know the answer. Okay. I mean, so we'll get the change in Celsius scale as what? 40 is the answer. Let's move next. Now, if we little bit revise it from the topmost topic, so we have converted, we got this thing. I mean, you know how to convert the any random, if suppose there is some random temperature on the Celsius scale, you can now convert it from Celsius to Kelvin and then Kelvin to Fahrenheit. Even it's not just for the Celsius scale, Kelvin scale and Fahrenheit scale. You can convert for any of the random scales now, isn't it? So we have the equations which you have to remember. And this is the numerical number 1 which we have solved it. This was these are all the practice numericals having the easy level, the medium level and the hard level. Okay. We have also seen a fresh topic, which is a subtopic, that is a change in temperature. So we have the direct formulas to get the fast answers. I mean, suppose you are having a less time. So again and again, you will not go into the derivation. You'll be directly applying the formula and then be happy. You got the answer, get the marks, enjoy the holidays. So now, after this, now we'll be going to start a fresh topic, which is thermal expansion. Yes, so let me a little bit. So this is our topic now. Thermal expansion. Okay, let's start it. Before starting it, I just wanted to ask a question from you students. So the question is in front of you. Suppose you are having a sphere like this. This is a sphere in front of you on your screens. Okay. And one more sphere. Okay. And if I say, suppose the diameter of this sphere is d2 and the diameter of this sphere is d1. And these are basically in a metal sheet. Okay. So you can assume that this complete is in some metal sheet. So let me highlight this. So this complete structure is in some metal sheet. You can assume something like this. This complete structure is in some metal sheet. So this is your metal sheet. And here is your structure. Cool. Now the question arises, I mean, these diameters are not equal. Basically, D1 is greater than D2. And these are something as, you know, you can call these as two holes of unequal diameters. These are the holes of unequal diameters. Done. Now the question is this, suppose you're having a metal sheet you can see on your screen. This is a metal sheet structure. And in this metal sheet, you're having two holes, one of diameter D2 basically, and another of diameter D1 basically, where you can see D1 is greater than D2. Now it says that this complete structure is basically a metal sheet. Question says ki if this sheet is basically heated, if the sheet is heated, then what's going to happen? You are having 2 minutes to answer this question. What's going to happen if this sheet is heated? Any answers? See, if we perform the experiment for this, if I'm going to perform the experiment, it will be something like this. Both D1, let me increase the size a little bit. Both D1 and D2 diameters will increase. Both D1 and D2 will increase. This is your answer. Okay. Both the diameters are going to increase here. This is your answer. If we are going to heat this metal sheet, both the diameters will increase. Now let's move next. So now from this conclusion, we can say that for the metallic structures, if the heat is provided to them, there will be expansion in the material. Now from this statement, what do you get? If both the diameters are increasing, what does it mean? It means basically, it gives us a hint. Yes, there is a metal expansion. There is a metal expansion, whether it can be linear. We'll understand this in the further sessions. It can be linear, it can be aerial, it can be volumetric expansion. Okay. Now let us understand this thermal. Okay, let me choose the color. Not this. Thermal expansions in solids. Okay. Distance between any 2 points on a solid increases with increase in temperature. Suppose we're having a point A and a point B. And suppose the distance between these 2 points is X. And suppose this is enclosed in some, it's on some plate, you can say something. And if I heat the structure, if I'm going to heat the structure, so what do you think what's going to happen? If I'm going to heat the structure, what do you think? Basically, on this same plate, if I'm drawing the same dimensions, I think so. Basically, on the same plate, the distance between these 2 points will, yes, you're right, it will increase. Okay, because just in the previous on the previous slide, we have seen that the two holes, the diameters are basically increasing more individually due to the, it gives us the hint of thermal expansion or the metal expansion basically. So same will be applied for this too. Now based on this, I'll be asking you a simple question again. Yeah, we have already solved that question. So in the next session, we'll be understanding the types of thermal expansion. I mean, the types of thermal expansion. In the next session, we'll be understanding this, the type of thermal expansion. I mean, we'll understand that what is linear expansion, that what is linear expansion. We'll understand that what is, yes, aerial expansion. What is aerial expansion? We'll understand that what is volumetric expansion. what is volumetric expansion. Okay. For now, let's end the session. Thank you so much for, it's not end, it will be continued. Let me write it here. What end? To be continued. Okay. Thank you for your attendance in the session. So we'll meet in the next class. Till then, have a good day and thank you so much. I'm ending the class.